All right, in this lesson, we are going to introduce the parent functions. And so we have a table to kind of organize all the information, and each row has a different column filled in, but we're going to fill in all of them. And so I want to start with just the names of the function. And so this first function, the rule is f of x equals x. We recognize that as the linear parent function. And so to look at what some significant points would be, I like to organize them in a table. X, y. If I were to plug in -1 for x, we're just going to get -1 right back out. F of x equals x. So -1, -1, 0, 0, 1, 1, 2, 2. We could even do -2, -2. And so on a graph, it's just a line through the origin with a slope of 1. Hence the name linear. There are no asymptotes. And the domain and range, the domain, it's going forever to the left to -infinity, forever to the right to +infinity. So all real numbers. And then same with the range. It's going up to +infinity, it's going down to -infinity. So our range is also all real numbers. So linear, pretty easy, probably very familiar from Algebra 1. Next, we're going to talk about the quadratic function. And so the quadratic parent function is x squared. Okay, and so if we were to make a table of significant points, if we plug in -2 for x, if we square -2, -2 times itself is +4. And then if we square -1, we get +1. If we square 0, we get 0. 1 squared is 1. 2 squared is 4. So we're just squaring all our x's. And so on the graph, we have 0, 0, 1, 1, 2, 4. And then we have -1, 1, -2, 4. And so it creates this U shape called a parabola. And so something that helps me remember this is that there is a U in quadratic and it makes a U. For the linear function, line, it graphs a line. Okay, and then once again, there are no asymptotes. And our domain, this function is going to the left forever and to the right forever. And so our domain is all real numbers, -infinity to +infinity. And then our range, we could draw the bottom of a box here at 0, but it's going up to +infinity. So 0 to infinity. And notice I used a bracket because we do actually have that minimum point. Next, we see x cubed. That is called the cubic parent function. And this time, instead of squaring our inputs, we are cubing the inputs. So I'm going to pick the same inputs, -2, -1, 0, 1, 2. When you cube -2, it's -2 times -2, which is 4, times -2 again would be -8. So with the cubic function, you can actually get negative outputs. With the quadratic, all your outputs are positive because when you square a negative number, it becomes positive. -1 cubed would give us -1. Think -1 times -1 is 1, times -1 again would be -1. 0 cubed, of course, is 0. 1 cubed is 1. 2 cubed is +8. So on the graph, I'm going to start with 0, 0, 1, 1, kind of like quadratic. But now, when we do 2, we're all the way up at 8. So it kind of looks like a quadratic, but it's steeper, it's thinner. But on the left side, we can get the negative outputs, -1, -1, and then -2, -8. So it's kind of like a quadratic that's opening up, connected to a quadratic that's opening down. It makes this S shape. This point is called the inflection point. Anytime it changes direction of opening, that's called an inflection. And we'll talk a lot about that when we get to the cubic unit. So for now, you just need to know it makes this long S shape. Once again, no asymptotes. And then domain is very similar, domain and range is similar to linear. It's going forever to the right, forever to the left. And so our domain is all real numbers. And then just like the line, it's going forever up and forever down. And so our range is also all real numbers. Next, all they gave us was some significant points. So if you want to organize it in a table, kind of like we have been, X, Y, they're doing -2, -1, 0, 1, 2. That's what this plus or minus means. It's talking about the positive and negative. And so -2 goes to 2, -1 goes to +1, 0, 0, +1 goes to +1, and then +2 goes to +2. And so it looks like we have 0, 0, 1, 1, 2, 2, just like our linear function. But on the left side, we have -1, +1, -2, +2. So it doesn't just take the input and give you the same input back. It takes your input and gives you the positive version of that input. And so whether it's positive, your output's positive. If it's negative, your output's still positive. And so this is actually called the absolute value function. And the symbol for absolute value is 2 vertical bars, absolute value. And whenever you see those bars, it means take the positive. So, for example, absolute value of -3 would equal 3. And you would see that point right here. And so it makes a V shape. And so the way you can remember that is that absolute value has a V in it, and it makes a V shape. And it's very similar to our quadratic function as far as the domain and range goes. It goes forever to the left, forever to the right. So our domain is all real numbers, -infinity to +infinity. And then our range is also, oh, just kidding. Our range, just like the quadratic, starts at 0 and goes to infinity. And so starts at 0, goes to infinity. No asymptotes. We haven't seen any asymptotes yet, but we're about to. And so this function has 2 asymptotes at x equals 0 and 1 at y equals 0. So x equals 0 is a vertical line. Let me use a different color. X equals 0 is a vertical line. Here's your x equals 0 line. Here's x equals 1, x equals 2, x equals 3. That always throws my Algebra 1 kids off. X equals 0 is a vertical line, even though this is the x-axis. And so x equals 0 is your vertical asymptote. And then y equals 0 is our horizontal asymptote. Here's the y equals 0 line. It's right on the x-axis, just like this would be your y equals 2 line, y equals 4 line. So think of where it's crossing on the axis, which axis it crosses. That's what defines your equation. Okay, and so that would give us a horizontal asymptote. And so the only functions that have 2 asymptotes like this is actually your rational function, your rational parent function. And so that function is 1 over x. This time your variable is in the denominator. And so if we're thinking of some significant points, if I plug in -2 for x, I just get -1/2. if I plug in -1, 1 over -1 is just -1. If I plug in 0 for x, we get something that is undefined. And so we actually can't plug in 0 for x because 1 over 0 is undefined. If you were to type that in your calculator, you would get error, undefined. You're not allowed to divide by 0. And so that's why x equals 0 is a vertical asymptote. You're not allowed to plug it in. Okay, and so on the other side, if we plug in 1, 1 over 1 would just be 1. And then if we plug in 2, 1 over 2 would give us 1/2. Okay, and so 1 over 2. And so we can also plug in fractions. You might be noticing that you kind of just flip whatever you're plugging in. So -2 goes to -1/2. 2 goes to 1/2. If I plug in 1/2, I'm going to get 2 because 1 over 1/2, you divide by a fraction by flipping and multiplying. Multiply by the reciprocal. So that's just going to give me a 2 back. And similarly, if I plug in -1/2, I get -2. Okay, and so let's see what this looks like on the graph. And so let's plot the easy points first. -1, -1, and 1, 1. And then we have 2 1/2, and we have positive 1/2 goes to 2. And then we have -2 goes to -1/2, and -1/2 goes to 2. And so this function is kind of approaching the vertical asymptote, and then it's also approaching the x-axis. If you think of plugging in larger values, if I plug in 3, I'm going to get 1/3. If I plug in 4, I'm going to get 1/4. If I plug in 6, I'm going to get 1/6. If I plug in 100, I'm going to get 1 over 100. And so we're getting really, really close to 0, but we never actually equal the 0. And then same underneath. We're approaching that vertical asymptote. And then as I plug in -3, -4, -6, I'm getting really, really close to 0 from below, but never actually equal 0. There's nothing you can plug into this function to equal the 0. You can get really close. You can plug in 1,000,000 and get 1/1,000,000th, but you're never actually going to reach 0, which is why we have a horizontal asymptote at y equals 0. So I use HA for horizontal asymptote, VA for vertical asymptote. And so the rational function has 2 asymptotes. You can't plug in 0, and you can't get 0 as an output. And so that's why the graph looks that way. Kind of splits it up into these 2 little branches of the function. And so for our domain, we can have all real numbers except this x equals 0. We go all the way to -infinity, and we get stopped at the vertical asymptote, but then we pick back up and go on to positive infinity. And so it's still going from -infinity to infinity. We just have to skip over the vertical asymptote. And so we kind of talked about this with interval notation. If we want to exclude 0, we would do -infinity to 0, and then union 0 to infinity. You have to use those parentheses to make sure you're skipping over the 0 and not including it. And so the same thing happens with the range. We have from -infinity all the way to the horizontal asymptote, and we skip over it and then go on to positive infinity. And so -infinity to 0, union with 0 to infinity. I like using interval notation just because it's new and it's good to practice with that. All right, last one, we've got some significant points. We can look at it as a table. It looks like 0 goes to 1, 1 goes to 2, 2 goes to 4, and 3 goes to 8. And so this function is actually the exponential function. One of them. There's several exponential functions, but this is, exponential. This is one, and the rule for this, and some of you may have recognized it, it's 2 to the x. So if I do 2 to the 0 power, I get this 1. If I do 2 squared, or 2 to the first power, I get 2. If I do 2 to the second power, I get the 4. If I do 2 to the third power, I get the 8. And so on a graph, we have 0, 1, 1, 2, 2, 4, and then we have 3 all the way up at 8. And so some of you may remember this from Algebra 1, exponential. It's doubling as we go to the right. And as we go to the left, that means it's getting cut in half. So 1/2, 1/4, 1/8, and so on. And so just like the rational function, we're never going to actually equal the 0. We can get really, really close if we keep cutting in half, keep cutting in half, keep cutting in half, but we're never actually going to equal the 0. So this is another situation where we have a horizontal asymptote at y equals 0. Okay, and so for our domain, it goes forever to the left and forever to the right. Even though it's going up very steeply, it's still going to the right forever. So our domain is still all real numbers, negative infinity to positive infinity, but our range is a little bit different. We have this asymptote here that we never actually reach. And so our range, notice this entire function is above it. There's no piece down here like the rational. And so this is just 0 to infinity, kind of like half of the rational's range. You only have the positive part. Make sure you use a parenthesis because even though it looks like you're reaching 0, you don't actually reach this line. You just get infinitely close to it. Okay, last page. The logarithmic function, we have an entire unit on it. So this is really just an introduction. It's the inverse of an exponential function. And so the rule, and you may have seen this button on your calculator, you can have different bases, but we're going to look at log base 2 of x just because we looked at the exponential base 2. Okay, and so his table is just like exponential, only the x and y's are switched. And so I'm going to take all these x's and put them in the y's, 0, 1, 2, 3, and then take all these y's, 1, 2, 4, 8, and put them in the x's. And that's going to give us our log function. And so we have 1, 0, 2, 1, 4, 2, and then 8, 3. And so it kind of curves up to the right. And then just like exponential has a horizontal asymptote at y equals 0, instead the log has a vertical asymptote at x equals 0. Everything about the exponential is just flipped. And so this one has a vertical asymptote, and so it actually keeps going. I call it the tail. The tail goes down towards the asymptote. Okay, and so his domain and range are the complete opposite of exponential. His domain is 0 to infinity. Everything to the right of this vertical asymptote. And so 0 to infinity, and we never touch it, so we need a parenthesis. And then our range this time is all real numbers. It's going forever up and forever down. All right, next, this one is going to be a lot more familiar. If we look at these points, 0 goes to 0, 1 goes to 1, 4 goes to 2, 9 goes to 3. And so some of y'all may recognize that as square root. And so it's easy to recognize the log function because log log, it's in the name. Square root has a square root. And then you can remember exponential because exponent, x is in the exponent. Okay, and then to remember rational, rational is just another name for fraction. You're going to see a fraction bar. Okay, and so let's look at what these points look like on a graph. We have 0, 0, 1, 1, 4, 2, 9, 3 off our graph. So it kind of curves up to the right, a lot like log, only square root doesn't have a tail. Okay, he doesn't keep going. He has this blunt stopping point, and so the domain is greater than or equal to 0. It stops here and goes to positive infinity. So this time we have a bracket to infinity. And then the range is very similar. We start at y equals 0 and we go up to positive infinity. It goes up very slowly, but it does keep going up. And so our range is the same. And this function does not have an asymptote. And then cube root, just like square root, only instead of unsquaring things, we're uncubing things. That's what that 3 in the index is for. It's called the index of your radical. You can do a 4th root, you can do a 5th root, you can do any root you want. So a cube root uncubes things. And so when I'm picking significant points, I want to pick some perfect cubes. And so maybe some of the ones we saw up with cubic, we could pick these as our inputs, and then we would get the x's as our outputs. This is the inverse of cubic. Okay, and so I can cube root -8 and get -2. I can cube root -1 and I would just get -1. If I cube root 0, I get 0. The cube root of 1 would just be 1, and the cube root of 8 would be 2. And so we still have the point 0, 0, 1, 1, -1, -1, much like the cubic function has these 3 linear points. But instead of going up and way down here, 8 and -8 are our x's. And so we're way over here. 2 is the y value. So it goes up to the right, kind of like square root. But then we have -8, -2, so way down here. And so cube root has the same shape as cubic, only cubic is the long, skinny s, and cube root kind of looks like square root. It's a short, fat s. And so that's how I remember it. Cube root looks like square root, but he's got the other part of the s. Cubic looks like quadratic, but he's got the other part of the s. Right, so no asymptotes, and then also domain and range is super easy. It's going forever to the left and forever to the right. So all real numbers, -infinity to positive infinity. And then the range, even though it's very wide, it's still going up forever and it's still going down forever. And so our range is also -infinity to positive infinity. Okay, and so these functions on the last page are really our inverse functions. This is the inverse of exponential, and we'll talk about inverses in a later lesson. Inverse is basically your undo. It flips your inputs and output. This is the inverse of quadratic. It unsquares things. And this is the inverse of cubic, which makes sense. It undoes a cube. And so as we go through these functions throughout the unit, we're going to start with linear, quadratic, cubic, absolute value, and rational. And then next semester, we're going to look at all their inverses, log, square root, cube root, and we'll look at exponential with log because they kind of go together.